thought about what happens when you click on an icon? I mean, how does that simple action actually make a program appear on your screen? Or how does a game know how to save your progress? Well, it all comes down to this hidden conversation, a kind of secret handshake that's constantly happening deep inside your computer. So, what is this secret handshake? See, here's the thing. For the safety and stability of your entire system, a regular program, like your web browser or your favorite game, can't just do whatever it wants. It can't just reach out and grab a piece of hardware directly. Nope. It needs to ask for permission in a very specific, very controlled way. To really get this, let's use an analogy. Think of your computer like a big, busy restaurant. The programs you're running, those are the customers out in the dining room. But the operating system's kernel, that's the kitchen. It's a restricted area. And for good reason. That's where all the powerful stuff, all the raw ingredients, the actual hardware, is kept. And this separation you see here is absolutely crucial. Out in the dining room, the customers, our user programs, can do their thing, but they are strictly forbidden from entering the kitchen, the kernel. This isn't just a suggestion, it's a fundamental security rule. It's what stops a buggy app from, say, accidentally wiping your hard drive or trying to spy on another program. The kernel is the gatekeeper. So if a customer can't go into the kitchen, how do they get any food? Well, they call over the waiter, right? And in our computer restaurant, that waiter has a name, the system call. It's the official, safe go-between. The program gives its order to the system call, and the system call is the only one allowed to go into the kernel, into the kitchen, to get the job done. It's the only way to place an order, period. And that brings us to the more formal definition. A system call is the mechanism for a program to request a service from the kernel. Now, every time this happens, the computer has to switch from the program's user mode to the operating system's protected kernel mode. And yeah, that has a tiny performance cost, but it is the fundamental price we pay for having a computer that doesn't crash every 5 minutes. But here's the thing. You can't just ask this waiter for anything you can dream up. You can't order a unicorn. There's a menu, a very specific list of services that the operating system knows how to provide. And this menu is neatly organized into a few key categories, kind of like a 5-course meal. And here is that menu. The 5 main categories are process control, which is all about creating, stopping, and managing programs. Then you have file management for, you guessed it, working with files. There's device management, which lets a program talk to your printer or your mouse. Information maintenance is for getting system info, like the current time. And finally, communication, which is how different programs can talk to each other. Think copy and paste. Okay, let's dive in. We've seen the different sections of the menu, so now let's look at some of the most popular dishes, the common system calls that you are ordering thousands of times a day without even realizing it. Let's start with something you do all the time, launching a new program. You double-click an icon, and poof, it opens. But what's really going on behind the scenes is this beautifully coordinated dance of multiple system calls working together. The very first order is a system call called fork. Quick reminder, a program is just code sitting on your desk, but a process is a program that's actually running. So, an existing process, like your desktop environment, calls fork to ask the kernel, hey, can you make an exact running copy of me? This copy is called a child process. It's like asking the waiter to set up a new identical place setting right next to yours. But wait a second, you didn't want another copy of your desktop, right? You wanted to open your web browser. That's where exec comes in. The brand new child process immediately makes another system call, exec, which tells the kernel, okay, now replace my entire being with this new program. It's like the new guest at the table immediately changing their order to something completely different. So what's the original process doing this whole time? Well, a lot of the time, it'll use the wait system call. This is like telling the kernel, just pause me for a bit. Wake me up when that child process I just launched is finished. This is incredibly useful for things like scripts, where you need one command to finish completely before the next one can even start. Okay, so launching programs is one thing, but what about the absolute bread and butter of all computing? I'm talking about opening and reading files. This is something that happens constantly, and it all relies on that file management section of our system call menu. First up, your program calls open. It passes the name of the file it wants to the kernel. The kernel then does all the heavy lifting. It finds the file on the disk, it checks if you have permission to access it, and gets it all ready. If everything checks out, it hands back something called a file descriptor. Think of it like a little numbered ticket, a claim check for that specific open file. So, now that you've got your ticket, you can actually use the file with a read system call. You hand that file descriptor, that ticket, back to the kernel and say, hey, using this ticket, please give me the next chunk of data from this file and put it right here in this spot in memory. And the kernel does exactly that. All right, so our program has launched, it's read its files, it's done its job. What now? Well, just like a good restaurant guest, a program can't just get up and leave a mess. It needs to clean up after itself. And you guessed it, there are system calls for that too. The polite way for a program to end is with the exit system call. This is the program basically raising its hand and telling the kernel, I'm all done now, thanks. The kernel then swoops in, frees up all the memory, closes any open files, and releases all the resources that process was using. The table is now clear for the next customer. But what if a program isn't being polite? What if it's frozen solid, just sitting there causing problems? That's when we might need the kill system call. Now, despite the dramatic name, it's really about sending a signal to another process. Most of the time, that signal means terminate yourself immediately, but it can mean other things too. This is our restaurant manager stepping in and telling a disruptive customer, you need to leave now. Okay, let's zoom back out. We've looked at a few specific orders, but what's the big picture here? Why is this whole system of waiters and kitchens and menus so unbelievably important? Well, because this invisible layer, this system of constant requests, is the absolute foundation of modern computing. I mean, just try to imagine a world without system calls. Programs couldn't launch other programs. You wouldn't be able to open or save a single file. Your keyboard, your mouse, useless. Programs couldn't talk to each other. The operating system would have zero control. It would be pure absolute chaos. System calls provide the order, the security, and the structure that makes everything else work. So the next time you open an app or save a document or even just wiggle your mouse across the screen, just take a second. Think about that invisible storm of activity happening under the hood. Billions of requests being made and fulfilled, all thanks to this elegant secret handshake.